Hi everybody, today we're going to study and learn about inductance and specifically about this beautiful thing which called toroid. Okay, so what is actually a toroid? It's really important in many aspects of engineering. You can think about the medicine and also music and even in changing voltage, you're going to learn it at the future. And this device actually can capture and hold magnetic fields. Like we had capacitor, which can hold electric field. So this device can hold a magnetic field. So let's draw our inductor. Let's draw our specific toroid. There's many configurations of inductors. As you saw for capacitor, that you have many kinds, different geometry, different material property. The same thing with solenoid and inductors. It's the same idea. So this is a specific example that we're going to focus today, and I expect you to generalize and understand the idea how it works by the example. So in general, we have this inner core, which is look kind of like a donut. And what is the dimension? Let's draw another upper view. So this is actually R1, and this is R2. And for convenience, we're going to say that this distance is actually B. So the difference between R1 and R2 is B. And what I do to this coil, I actually taking a wire and I start to coil it up. Okay, so I have here wire and I continue to another loop, to other loop, to other loop, to other loop. And there's many loops surrounding this donut, okay? So many loops. How much? In a general case, let's say N coils or N loops around this core, okay? You can see it here, it's looking like this, right? This is the wire that I'm turning this one around. And you can also think about that if I apply voltage to this current, in the end, you know, it's something like this. I have your battery, right? So apply voltage to it. So what is the direction of the current? So the direction of the current is actually, in my case, going in. So the current, if I'm looking for above, is coming to the middle, right? So here it's actually, you can think about it that it's going in, right? And afterwards, the currents actually go outside. So this is the directions. This is the directions of the current inside it. And the first question I want to ask you is what the direction of the magnetic field? So my question to you is, what is the direction of the magnetic field inside this toroid? Okay, so let's draw this concept. Let's clean this one. So let's draw the profile of the toroid. So the profile of the toroid is pretty simple. It's a square. This is a square. And it's continue, right? I just took a piece of it and we have the wires surrounded it, right? The wires surrounded the shape. And what is the geometry of it? So here we had height h, let's say. And we know that this is R1 and this one is R2, but we said that this distance is actually B, right? So this is the configuration we have. So if we want to understand directions when it's come to magnetic fields, what rule do we have? The right-hand rule, right? So if we have a current that's going in that direction, so what I expect it to be, so I'm looking here and I'm following it, and what I see that the magnetic field is going into the board and outside the board. So this one contributes this. And here it's doing that. Let's do it in a different color. Let's do blue. The blue we already used. Let's do green. Okay, so this one is green. And I go to the other one. What do I see? Oh, the same thing. Okay? And I'm going here. Oh, the same thing. And outside X. And here what I see? Oh, the same thing. So what I actually have here, I have an enormous magnetic field inside. since I have a lot of wires, a lot of wires. So each section of the toroid, if we're gonna take, that's what I did. I take the toroid and cut it, okay? So each section of it actually contains a lot of dense magnetic fields, okay? So this is the concept. So if you're gonna give an axis, if I'm gonna give the axis to the drawing that we had before, right? To this one, let's do this X, right? Let's clean it a little bit, right? So this one is Y, and this one is X, right? So here, so actually the current is actually leaving side here. So it's in the theta direction, right? That's what's going on here, in the theta direction. Perfect. It doesn't mean, okay, that's the concept. Perfect. So after we talked about what is the direction of the magnetic field, so the magnetic field is tangentially, right? So in the theta direction. And of course, I can change it to be in the positive or in the negative, depends on the current, right? If I'm gonna change the battery here, if we're gonna change the battery, I have two wires in the end, right? I took wire lead, and then I have what's left over. If we're gonna switch the battery, it's gonna be the other way around, right? Because the hand's gonna look like this, right? So it's gonna be X instead of dots. Until here, everything is clear? Okay, so I don't hear you. Everything is clear?
Yeah, it's clear.
Yes, okay, I hear you so soft. Again? Can you say something?
Yeah, it's clear.
No, I hear you just a little bit. So if you have a question, let's use the chat, okay? And so I open the chat. So the second question is gonna be, what is the size of this magnetic field, okay? And this is kind of a recap. So what is the size? So I'm gonna take off this drawing. So my section B question is what is the magnitude of the magnetic field? Okay, so what two options do I have to find size of the magnetic field? I have two options, right? I have Bio-Savart, right? Bio-Savart, and I have Ampere. So let's use Ampere law in this configuration because of the symmetry. I have an idea what I want to do with Ampere. So what is the formula for Ampere? Ampere law. Where is the razor? Here it is. Okay. So I'm gonna write the equation. So the equation states that if I choose a closed loop on the magnetic field and do the dot product between the line of the magnetic field, right? So what I want here to have a really easy dot product, which means I want alpha to be 0 or pi over 2, right? Something that's gonna be easy. Or maybe you know a 2 pi or 3 pi over 2, but something that it's really easy for me to solve. This is the loop that they're gonna choose. Close loop, okay? And this must be equal to what? To the permeability, right? Some constant related to magnetism, and also all the currents that penetrate this area. So if I choose, for example, heart as my closed loop, which I can do it, so I10 is actually gonna be all the current that actually going inside this heart and pocket, right, and penetrate it, okay? Perfect. So let's choose a direction. So if I know that the magnetic is always tangentially, so it's gonna be really easy for me, let's clean this one up. It's gonna be really easy for me to choose the loop to be like this, right? It's not the green. The loop right now is in green. So the loop is like this. right? And the magnetic field is in theta direction, right? So let's do this. So I actually can say that I don't know what is B. I don't know, but B, from symmetry reason, it must be a function of R, right? It's changing only the distance, because if I look at this direction, or this direction, or this direction, the world is looking the same. So now it must be a function of R, okay? And also, I know that it's in the direction of theta. DL, the loop that I choose, okay, is this circular thing, right? So how can I exhibit this length in a more mathematical way? I can use DL as R, sorry, not this capital R, it's small r, it's a general R, is the R of this loop that I choose. R d theta, right? The radians, this is small angle, d theta. So this thing, and what is the direction? The same. So when you have this kind of thing, I know that, yeah, it's gonna be easy. The angle is the same angle, so we have the same thing. So this actually kills itself in a dot product, right? So we end up in B. We end up in B as a function of R multiplied by R. So that's what we have on the sorry, and we did the integral, right? Forgot about the integral. So it's running from 0 to 2 pi I, 2 pi, which means a full circle. So we actually end up here with 2 pi R, right? Perfect. So we have the right hand side of the equation. So right now what we need to do is actually find the other side of the equation. So the other side of the equation is asking, what are the currents that actually penetrate this area? Which area? This area. This area, right? So if I look at this toroid, and I put my loop inside the toroid, I see that all the currents, that all the wires are actually connected like this, right? And getting inside, like this, and getting inside, like this, and getting inside, like this, and getting inside. Okay, so the part that's going inside is actually what's penetrating. So I have mu0, but I have many eyes, right? To penetrate in. How many? I have n coils, so I have n eyes. So actually, this means that we end up with having mu n I equal to this thing, right? So we're getting that B inside is equal to this divided by this. So mu 0 n I divided by 2 pi r. So this is the magnetic field inside. If we want to be more generalized, we can take off this in and say that this is when R is in the middle of this toroid, right? What's going on outside? Okay, what's the magnitude of the magnetic field outside of the toroid, right? For example, let's take the example of this. Let's look what's going on here. This we have two outside, right? We have this, and we also have in the middle, right? Where here you have nothing. So we have this and this. So let's try to figure this one out. So I'm cleaning this picture. Okay. So I have this toroid. This is my toroid. And now I choose my loop to be this loop. Oh, this loop outside. See it? This is the loop. This is DL, right? So actually, the right-hand side stays the same. You see, I choose the loop to be what? A perfect circle. That's what I choose it to be. And then I said from symmetry, it must be a function of R, and it's still in the theta direction, right? And I have here, this is my DL, so it ends up to be 2 pi R, so this side is the same. Let's see what's going on with this side. And look at this side, I said, there's many currents that penetrate. I have this one that penetrate, but I have also this one in the other direction. You see? The current goes from here, penetrate my area, this is my area right now, all of this. I have all the toroid to myself. So I have this one that's actually coming into me, and I have some current above me, which I don't care, but then again, oh, it's entering inside. You see it? And how many times this is happening? A lot of times. How many coils do I have? N. So I actually here need a correction. I have some currents that's coming in, I in, right? Which is the excess, right? And I have minus someone that's going out right here. So this is out. But they're the same wire. You got me? They're the same currents that going in, is the same ones that go out. And this happens n times. So we actually have n times multiplied by 0. That's what we have here, right? Because each time they cancel the effect because they're coming from other directions, right? So here it's actually making, sorry. So this solution actually says this. I have this term equal to 0. I can divide by 2 pi r, and this is equal to 0. Outside, out, right? And why this is happening, I can do that, be really careful, because of the symmetry. Okay, because of the symmetry, I state that the magnetic field is only tangentially this problem. Okay, so for that assumption, I can make this statement because I can take out of the integral thing. That's what happened here. Take it out. Here it is, and this is what that's what they do. Got it? Perfect. Let's talk about the smaller loop. What's happening? Clean it again. What's happening when I observe this? The inner part of the toroid. Here it is. This is my axis, right? And I'm looking right now at this one. Oh, what's happening here in the middle? So I do a small loop, right? I said that everything is small loop. The right hand side, stay again the same. It's a loop. Delta is tangentially, can go out, and I have 2 pi r. This is the same. But tell me what's happening here. Who are the currents that actually penetrate my area? This is my area. Up, 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 up. So who dare to penetrate it? This is the current, right? It's coming at me. Poke nothing because my area is not here. Come here, go inside, not penetrate anything. My area is here, right? It's not including this part. And then you go to another round. Again, going to another round. Again. So no current at all penetrating. There's no sigma of I minus I. It's here actually already 0 in this state. So for the same reason as we had before, not the same reason, it's a different reason. Right now, the reason is because there's no current at all. And before it was that the currents actually cancel each other out. So we again have that for R smaller than R1, it's equal to 0 as well. So we can say in general that P out is 0, okay? Perfect. So right now, I want to focus more about the toroid. We understand the magnetic field, and we learn a lot of interesting ideas about magnetic fields. So let's clean this board out, okay? And let's draw how the magnetic fields look like, right? So in general, we know that if this is my toroid, right? So this is my toroid, okay? I cut it, right? This is the empty part. Let's do it like empty. There's nothing here. Actually, here you see the wires, right? You see the other wires coming. This is the wires. And here you have this kind of wires over here, right? And also here it's looping it. So I just cut, let me draw it again. I did this drawing. I cut the toroid in that direction and put it in front of you, right? So this is like the wires. So this part is actually this part, right? And here is this two. So we said that the magnetic field is actually V inside. We said it tangentially, right? And it's looking like this, mu0. When I say in, let's be more specific. I mean R1, R2, right? So it's mu0 and I, the number of coils and the current that I put inside, and it's die out in that fashion, right? So which means that I have some kind of this effect, right? This is the magnetic field. This is its strength, right? It's a function of R, right? So this is the magnetic field's magnitude. And what is the direction? The direction is inside it, in the theta direction. It's going like this, here it's going like this, right? That's what we saw, right? Perfect. So that's what we have in a summarization. This is B as a function of R, B magnitude only as a function of R. This is the direction. So we understand what's happening in coils. Coils actually hold a lot of magnetic field inside, and outside of it, it promises us that the magnetic field, the out is 0. Perfect. So let's go to the next question, which is, what is the flux? Remember, magnetic flux from only one coil. Here it is. I have one loop, only one loop of I, right? So what is the magnetic flux over here? So what is, let's ask, what is the phi b from French, remember? That's how I remember it, phi b. What is the magnetic flux from one coil? Okay, only one of them, only one loop. One loop, single loop, single loop. Okay, so what's the definition of the flux? The flux, magnetic flux, is asking what is the sum of a lot of a small contribution to the flux. That's what we said. And each one of them is actually taking the area integral between B vector dot dA, which means this one is a small, is a flux, small flux. Okay, so the idea is this loop has some area that's divided to dAs, for example. So each one of them have an area dA. It's pointing in the normal direction. I have to think about it as a nose. There's a nose. This is, for example, dA. Okay, and the magnetic field is actually coming out of this area. For example, let's say in this direction, B. Just joking, it's not in this direction, right? So what is the flux between them? So let me remind you, what is really the direction of B? B is actually tangentially, right? It's inside, so it's actually also normal to the loop. Let's do the coil in other direction. So if this is the coil, so dA is pointing in this direction, dA hat is actually the theta direction, and also B. And also B. So we actually can easily solve this. So this dot is actually disappeared, and we have only the size multiplication. B can come outside because B equal, B cannot go outside. Sorry. Y cannot go outside. Let's think about it. So this is actually, why did I delete clean it? Okay, so this is my area, right? This is, each one of them is the dA, right? And in each location, in the radial direction, B is changing. We saw that it's actually dying out. You see it? It's dying out, okay? So let's actually write more explicitly this integral, okay? Let's do it here. So the flux is actually equal to this integral, to the integral of B dA, say that they are the same direction, and B is actually this one, mu n I over 2 pi r. This is B, is changing. And what is dA? dA is a small movement in the r direction, so we have here dr, and a small movement in the height. Z, let's call it Z, dz. Okay, so we have two integrals. One is from R, and which are relevant? Be careful. Not, this part is not really where is the area of the coil, right? The area is only this part, right? So we're actually running from R1 to R2. So this one is R1, R2, right? And what is dz? Dz is the height. So it starts from 0 to h. Okay? So this is the integral we need to solve. Yeah, I cleaned this one. And we have a lot of constant we can take out, not changing in R and Z, which is mu0 and I 2 pi, right? Also Z. So I can already multiply by h. And I do have an integral 1 over R, R1 to R2, dr, right? And this one is ln of R2 divided by R1. Why so? Because if I subtract ln R2 from R1, I can write it as a division of the two of them. And perfect. So we actually have a small, we have the flux from this window, from this loop. What is equal to? So phi b equal to mu0 n I h 2 pi ln R2 divided by R1. Perfect. So now I want you to think about it, that actually the coil is not ending as a square, just an approximation, right? Because the coil, the wire is actually going around and then going to the next loop, right? And then to the next loop, 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 and then to the, until you do all the circle, right? That's what actually happened. So if I want to find out what is the total area, it's the total area is in approximation, right? So the area of this loop actually hold, right? This wire actually making a really weird shape of an area. So what I wanted to say that actually this flux is right, it's the flux of only one window, but actually the flux, the magnetic flux of a solenoid, it's of this kind of toroid, it's crazy. It's a huge area, right? This is the idea of this kind of loops, okay? So if I want to know what is the total flux of the toroid, not only single square coil, right? Not a single one, but all of them. This is the power of solenoid, okay? So let's do it. So, and the next question is, what is the flux? The same question of the toroid, of the all toroid, which toroid, sorry, toroid. So what is it? And in general, we understand we are talking about that phi b total is actually the sum of all this squares loop that I have. I have this one, 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 and surrounding. That's the idea of the toroid, right? I have many of those. So in general, I can say that this one is equal to the sum of all the small windows that we already found, right? And how many windows like this do I have? This happening every angle, right? So this is happening n time, right? N times because I have n loops, right? So this one actually n multiplied by this. And if I'm going to multiply, then you see that I have here already n because I found the magnetic field. So this one becomes square. Okay, so this one is multiplication and multiply phi b old. Let's do single loop. Coil with only one loop. This is the real thing. Okay? So this flux is mu0 n squared I h 2 pi ln. I'm putting I at the side, okay? You're gonna understand in a second why I did it. H ln R2 R1. And at the beginning, we had also I, the current, right? Okay, so in general, I want to ask you right now a new idea. Okay, you see what we did here? In general, okay, let's draw what happened in this question. So we found the total flux of the toroid, which is phi b. I'm going to call it total, and this one single loop, right? So I did kind of a superposition. So in general, what's happening when you're talking about solenoid, inductors, all this concept, you actually want to know what is the flux. That's what interesting us. Why? Remember Faraday law? We know that the flux is really interesting. We want to find. And to do that, we need to find the magnetic field, right? That we have. And this can be a really nasty business, right? It could be Ampere, Ampere, and it can be Savart, and it can also be involved in a lot of integrals, right? Integrals, geometry, right? The geometry can be, I don't know, it can be like we had this kind of shape, right? It could be cylinder, it could be many things, geometry, and also can be material properties. Material properties. For example, we don't have to have mu. We can have, usually in the coils, they put inside the material some materials that actually can observe magnetic fields, such as iron. You know that you take an iron and put it next to a magnet, oh, the iron became a magnet temporarily, right? So they put different material properties, and to find B, what we actually need, we need I, the current, right? Because according to the right-hand rule, we know that the current is actually what's producing the magnetic fields, right? This is called electromagnets. Electromagnets have current that produce magnetic fields, and this produce the flux. So you already see that this kind of a thing could be a pain in the ass. To do all this journey every time from the beginning, it's really hard. And you're already familiar with this process, right? Why are you familiar with this process? Because we have the same thing in other fields, okay? So what I want you to know is, instead of doing all of this, we can find the connection between phi, the flux, and on the other side, I, the current, and give this creature a name. And it ends up to be phi equal to L, that's the normal L, to L. This is L, put like a light around it, it's really important. L multiplied by I. And you already know this configuration. You have some physics property, and something in the middle, the talking about geometry and material property. You know it. Where are you from? When you know it? You know it, for example, in capacitor, we talked about it, Q equal CV, right? We had the voltage, and we have the charge, and we needed to go in the middle with Gauss, right, or Coulomb's law. So instead, we can talk about, you know, the geometry and the material property, epsilon, 0 epsilon r. So this one taking care of it. You also saw it where in Ohm's law, remember, V equal R I, right? What is R? R is rho L divided by A, area, length, and property, property of the material. I don't want to read this one. Okay, so, and you know what from other places? From physics 1, remember? You know that F equals M A. This is a vector set. What does this do? This do this, you know, it's the geometry, the volume of this mass, and also its mass density, how heavy it is, right? And you also know it from other places. I cannot stop. I have so many ideas. K delta x squared, right? You have it here. Okay, what spring I'm talking about, what's the geometry? So we have the same thing here. It's a concept that you are already familiar with. So every time they're asking you what this L of this creature, they're actually expecting you to do this. To do this, have the flux, to find the flux as a function of the current and asking you what's going on in the middle. So we did it. Here it is. Here it is. So we found the flux, we found the current, and we found something in between them. This part. So for toroid, you know, you can write in your formula sheet that you already calculate out what is L of the toroid, and you can see we have here geometry, right? It's a circular 2 pi h. The difference between the radius played again, how many coils do I have, right? And geometry, and we have the material property, which material I have inside of the toroid, okay, that observe the magnetic field. This is, of course, the constant of the vacuum, right? So this is the concept. So most of the time, you're gonna get L as a given, or you need to calculate it. So I recommend you to have in your sheet like some, I don't know, famous example of inductance like we had in C. Remember, the example is the for parallel capacitor, two plates capacitor, right? That's what I drew here. But you have also cylinder, remember? Cylinder, the oil problem that we saw. And you also can have a sphere inside the sphere, right? You have many configurations. So the same thing going on here. So, and after you know, when you know that this is the inductance, after you know it, we can actually calculate a lot of things. For example, let's calculate the energy of that I can store in this toroid. Okay, so let me clean this out. So, for example, what is the energy stored in the toroid? So what is the energy that's stored inside? So you saw in the lecture that the energy in a solenoid, in inductor, is actually a magnetic energy, and it's equal to half mu zero, half L I squared, right? So when you know this L, you can immediately know how much energy you can store. It's a function of the current. How much current I have inside will determine how much energy do I have if I know this constant, which related to the shape of my solenoid, my inductor, the shape of it, what material I have inside. It's all inside this. You don't need to do it every time again. This is the concept, okay? So it's actually a pretty easy problem for us. So we already found it. It's here. So in our case, YB is equal to half multiplied by mu zero n squared h divided by 2 pi ln R1, sorry, R2, R1, right? Perfect, and multiplied by the current square. That's it. So we found it, found the energy. Another concept, you saw that we saw, if you don't saw it, so we're going to saw it in the next video. But for example, if I want to use Faraday laws, I have Faraday's law, and let's use Faraday law. Use Faraday law. If I want to use Faraday law with Cv equal IL, okay, and a method, if you want to remember this, I think about it, IL like Israel. IL, okay, 2 letters. So now you can remember C. Look at Israel. Okay, you can think about it. CV from France, fly to Israel. Okay, some stupid and method to remember it by heart if you want. I am really a big fan of learning the equation by heart. Then you become a smarter engineer. You see stuff, you immediately understand what is the size, what are the magnitude, what's going on in the problem, what I'm missing, what I need to find. So stupid way to remember. If you like it, you can keep it. And perfect. So what is this flux? So remember that EDL, This is Faraday's law. It will say choose a closed loop on the integral E dot dl. So do the closed loop of E dot dl. And this one must be equal to the flux changing by time with the minus because of length. Okay? So this one can be really easy calculated if you know L. If you know L, this is L. If you know L, it's really easy to calculate it, right? Because this one can be many things, right? This is depending on your geometry. Probably, most of the cases, this one is some electric circuit, right? Choose the loop of the electric circuit as you saw in the RL question that we saw. And this term is actually equal to minus D. Instead of V, I can put IL divided by dt, right? And if I say that the geometry and the material property does not change, like usually happen in electrical circuit, if I choose this to be my electrical circuit loop, so L does not change. The resistor stays in place, and the material does not change. Everything is okay. So L can actually jump out. So you have a minus L multiplied, and then here you have the derivative of the current. So you easily deal with this phi. Remember in Faraday law how hard we work on finding every time phi. It was really a challenge, right? So now you see how immediately you can solve the derivative if you know what is your inductance property. Okay, guys, this is all for today. I hope this tutorial open your eyes how much important is to actually define this property in order to save us time. Of course, you know, when you're gonna be more grown up and deal with some engineering problems, most of the time your inductance will be given. In this class, one of the goals is to understand what is the inductance, to know it by heart, to find it. So some of the questions deal with that. And this is a good practice for Biot-Savart or Ampere's law, right? Find it. And afterwards, you can use this information and find energy, flux, current, whatever you want, okay? So you know it, that's it, okay? So, and also you can connect other one. For example, if I had here some toroid, and this toroid is connected to another crazy shape device, I know that in general, this one have some inductance, and this one have some inductance. I don't need to solve everything from the beginning. I can understand they are connected in series to each other. So inductors actually sum up like resistors. So the effective one gonna be L effective. You can find it easily. So L effective gonna be the sum of the sum for series, and if it's gonna be parallel, so it's gonna be, you know, the sum of the 1 over, right? I minus 1. So you can also do this trick, okay? And to save time. So that's all, guys. I really hope that the class was clear to you. If you have any question, go ahead. I'm waiting for a few seconds. And if not, we're gonna finish for today. Okay, guys, thank you so much. See you next week. Have a good time. Have a good one.